Hey there, awesome physics students. Let's talk about equivalent resistances in series and parallel circuits. The idea with equivalent resistance is that you have a bunch of resistors in combination, either in series or parallel or some combination, and you're trying to smoosh those down and combine them to form one equivalent resistor that has the same effect as all those resistors in the configuration that they're in. So let's talk about the series case first. So in series, let's say you have your series circuit here. So you have your first resistor, and then you have your second resistor here, like that. So this is R1 and R2. And for this example, let's make R1 5 ohms, and let's make R2 2 ohms. Now what we want to do here is we want to combine these to an equivalent resistor here, like this. So it's one overall resistor in place of those, an equivalent resistance. Well, in a series circuit, it's fairly straightforward. You just combine the resistors by adding them. So it'd be the equivalent resistance is R1 plus R2 plus R3 if you had a third resistor, and so on and so forth. Okay. In this example, we have the 5 and the 2, so the equivalent resistance here would be 5 ohms plus 2 ohms, so that's 7 ohms. Now notice that that 7 ohms is going to be bigger than either of these two individual ones. Now that may make intuitive sense, but let's think about it before we just blindly compute. If you're a charge and you come out of the battery, you have to go through R1. You also have to go through R2. You have no choice. You have to go through both of these. If there was a third resistor, you would have to go through that one as well. And so adding a resistor will increase the overall resistance because all of the charges have to go through all of those resistors. Okay. Now the parallel case is a little different. So here's our circuit here. We have a resistor here. We'll call that R1. Let's make that one 3 ohms. And then we have another resistor here. Let's call that R2. And let's make that one 6 ohms. Now what we want to do is we want to make an equivalent circuit for that. That looks like this. So it's just one equivalent resistance, just like that. In this case, the parallel case, it's a little more complex. The equation is 1 over R, the equivalent resistance is 1 over R1 plus 1 over R2 plus 1 over R3, and so on and so forth. Okay, so you have to use your fractions here. In this particular case, let's compute it. It'd be 1 over R equivalent, which would be 1 over 3 ohms plus 1 over 6 ohms. Now these are fractions. I have to combine them like fractions, so this is going to be 2, if I multiply both top and bottom to get a common denominator, multiply both top and bottom by 2, this becomes 2 over 6. So 2 over 6 plus 1 over 6 gives me 3 over 6 ohms there. Notice the ohms is on the bottom here. I'm not done. This is 3 over 6 is about a half, but that's not equal to the equivalent resistance. I still have to invert this thing to get the equivalent resistance. So that I need to take this 1 over the equivalent resistance and invert it. Okay, so I need to take this to the minus 1 power here, and this gives me 6 ohms over 3. Notice that now the units are right. I have ohms on top instead of on bottom, and 6 over 3 is just 2. So the overall equivalent resistance for this one is 2 ohms. Now, we don't want to just blindly compute. We want to think about it after we do it, just like what we did here. Let's think about the path the charge takes, just like what we did over here. If you come out of the battery, you're a charge, you can either go through R1 or you can go through R2. If there's a third resistor, you could go through that one too. You don't go through all of the resistors. Notice this 2 ohm is less than either of these two. And in fact, it's the smallest resistor here is 3. It's less than that 3 ohms. When you add a resistor in parallel, that reduces the overall resistance of the circuit. So if I added a third resistor, let's say that resistor was 1 ohms, then the equivalent resistance here would be less than that smallest resistor. So it would be less than 1 ohm. If you add a path, that reduces the resistance because not all charges have to go through all of them. They can choose. Think about a physical situation that corresponds with this. If you're on the highway and traffic is backed up and there's a 6-lane highway, you often see people try to get through that traffic by taking a side road that runs parallel to the main 6-lane highway. Even if that side road can only accommodate 1 lane of traffic, so a tiny amount, a trickle of cars, the overall effect will be to increase, just slightly increase the flow of cars through that system. And so whenever you increase the flow, that reduces the resistance. So even a small side road can reduce the resistance. Just likewise, even a large resistor placed over here in in parallel with this would provide an extra path, and that would lower the overall resistance. All right, so just a reminder, don't forget to invert this after you're done, and also adding resistances in parallel decreases the total resistance, whereas adding resistors in series increases the overall resistance. All right?